Hello and welcome to section 5.3, the fundamental theorem of calculus. For this section we're going to make the connection between the antiderivative, which is what we learned about back in section 4.9, which was just the function that you get when you put the inverse process of differentiation on a function. And we're going to tie that to what we've talked about in chapter 5, which is the area underneath the graph of a function. So you'll want to remember or review the antiderivative table that we talked about in section 4.9. So the fundamental theorem of calculus is actually two parts. The first part is what ties the antiderivative, the area. So we're going to start off by defining this function, which is kind of strange looking. So notice this is a function of x, and x is what appears in the upper limit of this integral. And we have a function defined in terms of some other variable t, and the fact that there's this other variable, don't let that bother you. It's just, it needs to be distinguished from x. And so when we evaluate this function, we're putting in values of x by changing the upper limit of this integral. Values of t are not changing. So remember from last section that the definite integral gives us the area, the net area under a curve. So evaluating this function is going to give me a definite integral, and it's just going to give me each value of x is going to correspond to an area under the curve, the graph of f, for a particular value of x. So let's look at it a little bit more. So this is the area generating function, right? When you plug in a value of x, you get the area underneath f from 0 to whatever that value you plugged in was. So here I have f of t is going to be, I just picked a function of t cubed, and I picked that. You see it graphed here. And now g of x is that area generating function. And I don't know why the parentheses don't show up sometimes with Desmos, but they don't. So you can see that when there should be parentheses here, when I evaluate this function g at a constant b, it's giving me the area underneath this curve f. So for different values of b, all I'm doing is really changing the right endpoint of that interval integration here. So when I plug in that value of b, I'm just getting a new area every time underneath that function on a new interval. So one thing I want you to know is we've not graphed g here. We've just graphed f, and I am just evaluating g, and it's giving me these different areas for different right endpoints. Now look what happens if we take the derivative of g. So I'm going to let Desmos do that for me, and I'm going to set this new function h to the derivative of this area function. So when I turn on the graph of h, it's this blue dotted graph. And you can see that the graph of h is the same as the graph of f. So since h is the derivative of g, that means that g is the antiderivative, or is an antiderivative of h. But it's looking like h and f are the same, at least have the same graph. So we should start thinking that maybe g is the antiderivative f. So this is kind of giving us hints. So now let's graph g. So before we were just graphing the area output that g outputted, but now we're going to actually graph g. So g is graphed here, this purple function. And if I look at a point on g, you can see that its output is the same as the area under the curve of f, because that's how we defined it. This is the area under f. And it's also the y-coordinate of a point on G. So now we see what that function G looks like. And let's go look at something else. So now I'm taking an antiderivative of f. So this capital F is the antiderivative of f. And so when I turn that graph on, I see that that's the same as G. So there's more evidence that G is related to the antiderivative of f. So the area under the curve of f is somehow related to the antiderivative, and they look to be the same. They have the same graph. So we've seen two things here. We've seen that the derivative of G looks like f, which tells us that G might be an antiderivative of f. And then when I actually found the antiderivative of f with capital F, we see that it's the same graph as the graph of G. So this slide summarizes what we've seen so far. So it's looking more and more like G is an antiderivative of f. So let's look at an example of using this area generating function. So I have the function g of x, which is the area generating function for f of t, and here's the graph of f of t. And we're supposed to evaluate g at each of these values. So g of 0 is going to be the area under the curve from 0 to 0. So there is no area under the curve from 0 to 0. So g of 0 is just going to be 0. So now let's go look at these other values. So g of 1 means I am putting the value 1 as the upper limit of this integral into g. So when I evaluate g at 1, so that's g of 1, I'm getting the area under f from 0 to 1. And it's this right triangle of base 1, height 1, so it has an area of 1/2 so far. Now g of 2, so I'm going from 1 to 2, so I'm going to be accumulating net area. And so again, from 1 to 2, I have a right triangle with base 1, height 1. So I'm summing these, and I'm getting an net area of 0. G of 3, I'm accumulating area. Now I'm adding the area from 2 to 3. Again, it's another right triangle, and so on. And so you can see how now the area is negative 1/2. The net area, excuse me, is negative 1/2. So we keep accumulating the area underneath the curve. So notice when I go a g of 5, now I have something that's not just a triangle like I'd had before. So g of 5 is going to be, I'm going to add the area of this square, which is 1, plus the area of this triangle, which is another right triangle, vary 1/2. So g of 5 is going to add 3/2 to the area. And finally, g of 6, I'm going to add 2 of these squares and a right triangle for an addition of 5/2. So my total area under f from 0 to 6 is 4.